Okay. So in the last class, we were discussing about the what you call transients, right? The last class we were discussing about transients. So first order circuits and second order circuits. First order circuits and second order circuits. A quick review. Transients mostly you'll get from first order circuits. As I told you, you'll mostly get from second order circuits. So the four formulas that I told you, which are important, and those consists of your all the uh, theory of transients. Okay, so for if you see an RL circuit and RC circuits, there are only two formulas, or rather you can call four formulas: source free or with source, RC circuit, right? RC, you'll write I of t is equal to I of infinity plus I of 0 minus I of infinity e power minus t by tau. What is tau? Tau is equal to, in an RL circuit, tau is equal to L equivalent by R equivalent, right? In case of RC circuit, V of t is equal to V of infinity plus V of 0 minus V of infinity to e power minus t by tau. And what is tau? Tau is equal to R into C. R equivalent into C equivalent. Okay. If it is a source free circuit, what happens? I of infinity will be 0. Okay. And V of infinity will be 0. Source free circuits. Source free circuits. Then the formula will become I of t is equal to I naught e power minus t by tau. And V of t is equal to V naught e power minus t by tau. Source free circuits, only two steps. Find I naught, find tau. Find V naught, find V naught and tau. Okay. In case of with the source or a step response, you need to find I naught, I of infinity and tau. 3 steps. V naught, V of infinity and tau. 3 steps. Okay. 3 steps in case of RC and RL circuits with step response. 2 steps without any other external source. Source free circuits, 2 steps. Able to hear me, right?
Yes, sir. Yes, sir.
Okay. Next topic is SSSA or Sinusoidal Steady State Analysis. Okay, Sinusoidal Steady State Analysis or AC circuits. Okay, so or AC circuits. What is a sinusoid? Sinusoid is a signal that has a form of sine or cosine function. Okay, it may be sine or a cosine function, and it has very importance in case of electric circuits, that two AC circuits. Okay, AC circuit is nothing but a sine or a cosine circuit. Okay, and when you see this, this is how you write it. V of t is equal to Vm sine omega t. This is how you represent it. It's a sine or a cosine function. Okay, sine to cosine, I think you'll know those. So Vm is called the amplitude or the peak. Okay, this is called the amplitude or peak of the sinusoid. Amplitude or peak of the sinusoid. Vm is nothing but the maximum value. Okay, and omega or the positive or the negative max. Okay, positive or the negative max is called amplitude. Okay, omega is the angular frequency in radians per second. What is omega? Omega is the angular frequency in radians per second, and it is equal to 2 pi f, and f is frequency in hertz, cycles per second. This is radians per second, this is cycles per second. Okay, omega t is called the argument of the sinusoid. Omega t is called the argument of the sinusoid. Okay. AC waveform characteristics. Okay, the period t is the length of the time in seconds that the waveform takes to repeat itself from start to finish. See, all these are periodic functions. Periodic functions in the sense they repeat itself from the start to finish after a certain time. That is called as a time period. Okay, this can also be called as the periodic time of the waveform or sine for sine waves or the pulse width for square waves. Okay. So what is a period? Time period. Time period or the period is nothing but the length of time in seconds that the waveform takes to repeat itself from start to finish. Okay, this waveform is repeating. Okay, this time is called as time period or the period. Okay, then it is represented by t. Next, frequency is the number of times the waveform repeats itself in a second is called within a second is called frequency. Frequency is the reciprocal of time period with the unit being hertz. Okay, frequency is the reciprocal of time period. F is equal to 1 by t. Okay, it represents the number of cycles completed in a second. Okay, what is the frequency in India? 50 hertz, right? Frequency in India is 50 hertz. The amplitude is the magnitude or the intensity of the signal waveform measured in volts or amps. This is amplitude. Okay. Next, phase. The phase of an alternating quantity is defined as the divisional part of a cycle through which the quantity moves forward from a selected origin. When the two quantities have the same frequency and their maximum and minimum points achieved at the same point, then the quantities are said to be in the same phase. And said to be in the same phase. What do you mean by phase? Phase is the divisional part of the cycle through which the quantity moves forward from the selected origin. From a selected origin. That means if I take this as 0, what is the phase? Phase for this is 0. Phase is 0. This is 0 and 90 degrees. So the phase of this is 90 degrees. Phase is 90 degrees. That means it is the divisional part of the cycle through which the quantity moves forward from a selected origin. I took this as origin. Okay. Okay. When two quantities have the same frequency, and their maximum and minimum points achieve at the same point, and then the quantities are said to be in same phase. See, the frequency is same here, and this is quantity 1 and quantity 2. They are said to be in same phase when the maximum as well as the minimum points achieve at the same time and the frequency is same. Frequency should be same. That is important. Okay. Frequency should be same. Then they are said to be in same phase. Next, phase difference. Phase difference between two electrical quantities defined as the angular phase difference between the maximum possible values of the two alternating quantities having same frequency. So they should have same frequency to compare two sinusoids. Okay, if you want to compare two sinusoids, they should be like moving with the same frequency. Okay, then only you can compare two sinusoids. Next, in other words, two alternating quantities of phase difference when they have the same frequency but they attain that zero values at the different instant. The angle between 0 points of two alternating is called as phase difference. Phase difference is nothing but if this is 1 or A and there is one more at B. Okay, this angle is said to be phi. You can call the phase difference between A and B as phi. Okay, the points where they attain this 0 or but 5. Okay, maximum possible value or the 0 value is nothing but phase difference. Okay, lead, lag, and in phase. Lead, lag, and in phase. Okay, so lead and lag. So how do you define lead, lag? Lead is nothing but when which of these is leading, A or B?
A is leading.
A is leading B by
5.
actually it's B is lead. A is lagging B by 5 actually. No, sorry, correct. A is leading B by 5 degrees. Okay, or you can write B lags A by 5. That means B after 5 degrees, B is starting at 0. That means B is lagging A by 5 degrees. Okay.
Okay.
Or now A and B are said to be in phase. In phase with each other. That means their starting and maximum or the 0 and maximum points occur at the same instant. So they are said to be in phase with each other. This is A and this is B. When that what you call zeros and their maximum values or positive max and the negative max coincide, or the difference, phase difference between A and B is 180 degrees, then they are said to be out of phase with each other. Okay,
Okay.
in phase, out of phase, leading and lagging. Next, peak value, average value, and RMS value. Peak value, the maximum value attained by an alternating quantity during one cycle is called its peak value. It is also known as the maximum value or amplitude or crest value. The sinusoidal alternating quantity obtains its peak value at 90 degrees. Okay. Average value definition: the average of all the instantaneous values of an alternating voltage and current over one complete cycle is called average value. This 1 by T integral 0 to T f of x dx. Okay. The function from time period 1 by T 0 to T f of x dx. RMS value, that steady state current which when flows through a resistor of known resistance for a given period of time, that as a result the same quantity of heat is produced by an alternating current when flows through the same resistor for the same period of time is called root mean square value or RMS value. Okay, what do you mean by root mean square value? It produces the same quantity of heat through a resistor when the current is flown through a resistor. If it's DC, okay, it's DC equivalent of heat. Okay, steady state current which flows through the resistor of known resistance for a given period of time, that as a result of same quantity of heat is produced by an alternating current, steady current and alternating current, which one flows through the same resistor for the same period of time, is called as root mean square value or effective value of the alternating current. In other words, RMS value is defined as a square root of means of squares of instantaneous values. Okay, 1 by T integral 0 to T f of x square dx is RMS value. Next, there are peak factor. Peak factor is defined as the ratio of maximum value to RMS value of an alternating quantity. Form factor, the ratio of root mean square value to the average value of an alternating quantity is called as form factor. RMS value by average value. Okay.
Actually, where are these factors used mainly?
Okay. See, these are indicatives. Peak factor indicates the peakiness of a wave.
Okay.
Okay. Whether the wave is very steep or not. Okay. Depends upon the maximum value. If the maximum value compared to RMS value is very high, the peak factor will be more. Okay, that means the wave is very peak. It actually helps you in what you call setting up of frequencies. Okay, you can choose the wavelength and all. Form factor indicates whether you'll have the form of the what you call the wave form of the wave is nearer to a square wave or not. Okay. RMS value by average value. Okay, it gives you, if it's a square wave, RMS value and average value are the same, form factor for a square wave is 1. Okay,
Okay.
so that way you'll understand the formation of the wave, peakiness of the wave, like that. Okay.
Okay.
Hmm. Find average value, RMS value, peak factor, form factor of a pure sine wave. Try to find this. Average value, RMS value, peak factor, form factor of a pure sine wave. So what is the RMS value? So take V is equal to Vm sine theta. Okay, find the RMS value of the voltage. So RMS value is V is equal to under root 1 by 2 pi. 2 pi is the time period 0 to 2 pi. V square d theta or Vm square sine square theta d theta. Okay. This I can write as under root 1 by 2 pi. Okay. Or Vm square by 2 pi. What is sine square theta? Sine square theta can be written as
1 minus
1
cos 2
minus
theta
cos 2 theta by 2.
by 2.
What happened? T 2 theta by 2 d theta. So I can take Vm square by 4 pi. So what is the integration of 1 is 2 pi minus 0 theta minus cos 2 theta is sine 2 theta by 2 from 0 to 2 pi. So this will be Vm square by 4 pi 2 pi minus sine 2 sine n pi is always 0. So this will become pi gets cancelled. Vm by root 2. Vm by root 2 is 0.707 Vm. So RMS value Vrms is equal to 0.707 times the maximum value. Okay. Next, average value. Average value V average is equal to under root, sorry, 1 by T. See, again, time period. If I consider complete cycle, for a complete cycle, the average value is 0 because this is the positive value and negative value. If I take the average of it, it will be 0, right? Always. So I have to consider only the positive half cycle. So 1 by pi integral 0 to pi. Sorry, 1 by pi. Okay, I can take 1 by pi integral 0 to pi Vm sine theta d theta. This is 1 by pi or Vm by pi. Sine theta is minus cos theta 0 to pi. Vm by pi cos pi minus cos pi Vm by pi. This is 1 minus 1. So the sine theta is cos theta.
2 Vm by
What?
2
Yes,
Vm
it's
by
2 Vm by pi.
pi.
2 Vm by pi is V average. Okay. All what is the value? 2 by pi is 1 point. Sorry, average value is 0.637. 0.637. Okay. average value, peak, RMS value, peak factor, and form factor. What is peak factor? Peak factor is nothing but the peak value by RMS value, right? Peak value by RMS value. Vm by 0.707 Vm, or root 2 is 1.414. Okay, root 2 is 1.414. Next, form factor. Form factor will be VRMS by V average. VRMS by V average. That is 0.707 Vm by 0.637 Vm. That is 1.111. 1.11. Form factor is 1.11. Okay. Also, you have to remember for pure half wave rectified sine wave, these values are important. For half wave rectified sine wave, RMS is 0.5 times Vm. Okay, peak value is, or peak value is 0.318 Vm. Okay, sorry, average value. I'm sorry, this is average value. Next, peak factor. Peak factor is 2. Form factor is 1.57. These are important. You should always remember these. Okay. For half wave rectifier sine wave and the full sine wave. Square wave, all are 1, 1, 1, 1, 1. Okay. For a square wave, RMS value is 1, average value is 1. I'm sorry. Okay. Square wave. Okay. This is for HWR, half wave rectified sine wave. Okay. And for a pure sine wave, RMS value is 0.707 Vm. Average value is 0.637 Vm. Peak factor is 1.414. Form factor is 1.11. Important. Okay. You have to remember these. Okay. Sine wave, half wave rectified sine wave, and a square wave. Square wave, all are ones. So that's what I said. You peak factor shows, or sorry, form factor shows how how the formation is, and in compared to square wave. Square wave, it's always one. Okay. Okay, try to do this, assuming that the diodes are ideal, and the meter is an average indicating ammeter. The ammeter will read. It's an easy question. Try to do this. A, B, C, D. See, this is an HWR, half wave rectifier, right? So what is the current? We have VM. Sorry. We have VM as 4. VM is equal to 4 and R is equal to 10K. So what is current? As per Ohm's law, it's V by R. Vm by R is Im. Okay, so it is 4 by 10K is 0.4 milliamperes. Okay, but this is the maximum value. I need the average value. This is an average indicating ammeter. So what is the average value? 0.318 times Vm. 0.318 times. So find it. 0.4 by pi. Take it 4 into 0.318 is the average value, I average. Option D. Okay. It's an half wave rectifier sign, half wave rectifier because there is a diode. This is an average indicating ammeter.
So
Okay.
if it was as RMS indicating meter or something, then we should take RMS value.
Yes,
That
yes.
is
RMS value of half wave rectifier. Okay.
okay, 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 okay. So
So in meters also you'll be having average meters and as well as an true RMS meters.
true RMS, right?
True RMS meters. They call them as true RMS meters. So RMS value is nothing but the, as I told you, it's heat dissipation. It's equivalent to the heat dissipation in case of the supply is DC. Okay, that is
Right.
how they work actually. Okay.
Okay.
Next, you can find all these average and RMS values. Try to do this. I gave you the answers. Okay, it starts at pi by 4. What kind of waveform is this? Output of which? Output of which is this? If you are an electrical guy, you will know this. This is a
Actually, I'm not an electrical guy, but
okay. Okay.
some firing is something done.
Yes, yes, yes. In power
Thyristor,
electronics,
no,
yes, yes. Power
is it
electronics, you'll get to know this. This is what you call as what you call controlled rectifiers. This is an half wave rectifier, controlled rectifier. There is a firing. The what you call thyristor is fired, SCR is fired at pi by 4. Okay. This is how you do it.
right?
Okay. So you have to again see the RMS value again you have to consider from 0 to 2 pi 1 by 2 pi integral 0 to pi by 4 it's 0 plus pi by 4 to pi it is Vm sine omega t or sine theta. Okay. Then 0 again pi to 2 pi. Again, so only this value you'll get. Okay. This is a square under root. You'll get RMS value. Similarly, average value. This is how you have to do this. Okay.
Okay, okay, okay.
Next, phasor and phasor diagrams. A phasor is a complex number that represents the amplitude and phase of a sinusoid. Okay. Phasor is a complex number that represents the amplitude and phase of a sinusoid. V of t is V of cos omega t plus phi. Vm cos omega t plus phi. This is a time domain representation. This is V equal to Vm at Vm at an angle phi. This is called as phasor domain representation. Okay, graphical representation of these phases is known as phasor diagram. Okay, phasor representation is this one. And the graphical representation of these are known as phasor diagram. People usually gets confused. Okay, phasor diagrams are very important. Okay, all your electrical guys, the missions, power systems, everything revolve around phasor diagrams only. Okay, next. See, phasor diagrams, this is how you draw them. Okay, phasor diagram, this is how you draw them. Uh, so this is my real axis, and this is the imaginary axis, real axis and imaginary axis. So what you call the anti-clockwise or counter-clockwise direction is treated as positive angle, or the clockwise direction is treated as the negative angle. Okay, this is leading, this is lagging. Okay, leading and lagging. Okay, so if I rotate it in this counterclockwise direction, I'll get positive phase angle. Okay, if I say V is equal to Vm sine omega t plus phi. Plus phi means it is in this direction, leading direction, counterclockwise direction. Positive angle is always counterclockwise direction. Okay, so this is how you represent. Vm is the magnitude Vm sine omega t plus phi. Okay, this is common. Sine omega t is represented by this Vm sine omega t. This is the angle phi. Okay, this is leading. So if I say I, or you can directly write as V is equal to Vm at an angle phi. Okay, generally you'll write the RMS values, but for this case, I will be taking the maximum value or the peak value, Vm at an angle phi. Similarly, Im sine omega t minus theta. Sorry, I is equal to Im sine omega t minus theta. So this is the lagging one. The lagging one. Okay, Im minus theta will be always lagging. Okay, this is Im at an angle minus theta. Okay, so let me write down the time domain and phasor domain representations. So if I say Vm sine omega t plus phi, this can be written as Vm at an angle plus phi. Okay, or Vm cos omega t plus phi. This can be written as Vm at an angle phi plus 90 degrees. Okay, cos and sine. Tell me which one leads which one. What is sine and cos? Sine, if this is my sine wave, where will the cos side start? Cos wave will start.
Uh, like shifting the wave little bit left, like
Little
the
bit
top
left. What is the angle?
pi by 2.
Pi by 2. It start before the cos, sorry, sine wave. This is sine. This is my cos. Okay. Okay.
Right, right.
So which one is leading which one?
Here, cos is leading sine.
Cos is leading sine because cos starts earlier. Okay, is leading sine by 90 degrees. Okay, cos is leading sine by 90 degrees. So you can write cos theta is equal to sine 90 minus theta. Okay, cos theta is equal to sine 90 minus theta. So this can be written as sine 90 minus omega t plus phi, or minus Vm sine omega t plus phi minus 90. Okay. Okay.
Okay.
This is how you can write this. So complex numbers, you have two forms, polar form and rectangular form. Polar form and rectangular form. Okay. polar form and rectangular form. How to write in polar form and rectangular form? X plus JB or A plus IB, A plus JB are at an angle theta. Okay. Usually complex numbers are represented by I, but in electrical what we do, or networks what we do, we'll use J, because I we use for current, that's why we are using J here, okay, to avoid any confusion. So how to convert polar to rectangular or rectangular to polar? So from this R at an angle theta, what is A? A is equal to R cos theta and B is equal to R sine theta. Okay. In this way, what is R? R is equal to under root A square plus B square, and theta is equal to tan inverse B by A. Okay, if this is a sinusoid, R at an angle theta. Okay, this is my A, this is my B. This is real axis, this is imaginary axis. Okay. So this is how you convert from polar to rectangular and rectangular to polar form. R at an angle theta is A to A plus JB. Okay. Also if you just so if I want to add two complex numbers, okay, uh, 10 at an angle minus 30 degrees. Okay, or rather I'll take it this form. A R1 at an angle theta 1 and R2 at an angle theta 2. Okay, if I want to add them, add A and B. If I want A plus B, what should I do? Convert these into the complex conjugate form, like A1 plus JB1 plus A2 plus JB2, rectangular form. Then you can add A1 plus A2 plus J into B1 plus B2. Now you can convert it back to R at an angle theta, where R is equal to under root A1 plus A2 square plus B1 plus B2 square. Theta is tan inverse B1 plus B2 by A1 plus A2. Okay, if I want again, if A is equal to A1 plus JB1, B is equal to A2 plus JB2. If I want A multiplied by B, then again I have to use this form, a polar form, R1, R2 at an angle theta 1 plus theta 2. Okay, A by B, R1 by R2 at an angle theta 1 minus theta 2. Okay, this is how you do additions, subtractions, multiplications, and divisions in case of complex numbers. Okay, clear? Polar form and rectangular form.
Yes.
Try to do this. See, this is under root, right? Okay, under root, what happens if you square it, the angle will become double. Okay, if there is theta, it will become 2 theta. If you make it under root, it will become theta by 2. Okay, what is the star? Star means conjugate 3 plus j5. Conjugate of 3 minus j5 is 3 plus j5 complex conjugate numbers. Okay, so this is how you have to do this. Try to solve this. The numericals are not important. I just want to be clear on the process how to do from rectangular to polar and polar to rectangular. Okay, basically all the easy people are bit worried about these conversions and all. You should practice more to get used to it. Okay, basically networks is completely it's not a theoretical subject. It is it involves mostly on problems, and you'll get to know about the concepts by solving the problems. Okay, and obviously solving problems takes time. You need to spend more time for all this. Okay, and networks is a basic subject for many other subjects. So this is the one area you have to spend more time. Okay, so you find the average and RMS values for the following over a complete period: 2 minus 3 root 2 cos 10t plus 45 plus 3 cos 10t. Okay, so this is how you have to do it. Convert them. Okay, RMS value 2 is 2, 3 root 2 at an angle 45 plus 3 at an angle 0. So what is the RMS value for 2? 2 is same. Okay, and 3 root 2, 3 root 2 by 2, root 2, right? It is 3 at an angle minus 90 plus 3 at an angle 0. And this
Hello? Hello, sir. Hello?
you can add these quantities. Okay, the frequency of these are not same.
Hello, sir.
Hello, hello,
Sir.
able to hear me?
Yes, sir. Yes, sir. Right now I can hear.
Yeah, see, I was telling you how to do RMS value. See, first thing you have to observe is the frequency. What is the frequency of this? No frequency. Okay, this is 10t. The frequency of this is 10t, right? So these two are of same frequency. So you can add them. Okay, so how to add? The addition is simply this way: 2 minus 3 root 2 at an angle 45 plus 3 at an angle 0. Okay, 3 root 2 or minus 3 at an angle 0. You have to subtract it. Convert it into complex form and subtract it. You'll get 3 at an angle minus 90. Okay, so this is 2 minus 3 cos 10t at a minus 90 degrees. Okay, now RMS value under root, this is 2 square plus 3 by 2 or 3 by root 2 whole square or 3 square by 2. You'll get 4 plus 9 by 2 under root 8.5. Okay, if there is two different frequencies, you have to do it separately. 4 by root 2 and by root 2 square, 5 by root 2 by root 2 square. This is how you get it. Okay, the important thing is the frequency terms. They are of same frequency. You can directly add them or subtract them and do it. Different frequencies separately. Okay.
Okay, okay.
Phasor relationship of circuit elements. Okay, phasor relationship of circuit elements. So first one is resistor. Okay, V is equal to IR. Okay, I'll take I as Im cos omega t or sin omega t. I can take cos or sin. Yeah. I is equal to Im sin omega t. Okay, so this is what I'll get. V is equal to Im sin omega t. So I'll take it as theta. Im sin theta into R. So Im R sin theta. Let it be omega t. Just to avoid confusion, I'm taking it. Okay, Im into R sin omega t. You can call it as Vm sin omega t. So Vm is nothing but Im into R. R is equal to Vm by V. Okay. So if this is my, if I draw the phasor diagram, this is my voltage. The current is also in the same phase. So for a resistor, the voltage and current are in same phase, are on the same phase. For a resistor, voltage and current are in the same phase. Okay. Voltage is in phase with the current in case of a resistor. And in case of an inductor, okay, this is my plus minus V, this is I, L. So I'll take I is equal to Im sin omega t, I is equal to Im sin omega t. So we have V is equal to L di by dt, that is minus omega L Im cos omega t. Or
No,
sorry,
no, no minus is there.
no minus, right? I'm sorry. Omega L Im cos omega t. Okay, cos omega t can be written as omega L Im, okay, into sine omega t plus 90, right? Plus 90. Okay, so this is nothing but Vm sine omega t plus 90 degrees. So what is Vm? Vm is equal to omega L Im, or Vm by Im is called as XL, is nothing but omega L. This is called inductive reactance. Inductive reactance. Okay, XL is equal to omega L or 2 pi FL. Okay,
Uh, so
what?
actually, why have not we taken sine omega t minus 90? Like it's also cos uh, omega t, right?
No, no. What is
Hello,
omega t minus 90? Sin omega t
hello.
minus 90 is? Hello? Sin omega t minus 90 is? Hello?
Ah, yes, now it's audible.
Sin omega t minus 90 is minus cos theta.
Okay, okay, okay. Yes, pi by
Sin
2 minus.
omega minus 90. Okay.
Right, sir, right, sir, right. Yeah. Hello, hello.
Hello? Hello?
Hello? It's audible, sir. Now it's audible. Sometimes the voice is breaking.
I think so, yes. Okay. So if I take my current as this, I is equal to Im sin omega t. Okay, where is my V? V is leading I by 90 degrees. Okay, V is leading I by 90 degrees. That means I lags V by 90 or V leads V leads I by 90 degrees. Okay.
Okay.
Similarly for capacitor, V and I. I'll take V is equal to Vm sin omega t. I is equal to CdV by dt. So this will be like this. C into Vm omega cos omega t. Okay. So this will be, I can call it as Im sine, again same, omega t plus 90. Okay. So Im is equal to Vm into C omega. Vm by Im is 1 by omega c. That's nothing but xc, which is equal to 1 by 2 pi fc, called as capacitive reactance. Capacitive reactance. From this, if I take V as Vm sin omega t as reference, what is I? I is leading 90 degrees to V. Okay, I can say I leads V by 90 or V lags I by 90 degrees. Okay, in case of capacitor, I leads V by 90 or V lags I by 90 degrees. Okay.
Clear.
Okay, and XC is 1 by 2 pi fc or 1 by omega c. So, yeah, this is how you write it. R is equal to an impedance and admittance. R is Z, in AC, Z is only resistive networks, only R network. Z is R, impedance is R. Okay, admittance is 1 by Z or 1 by R. For an inductive circuit, it is Z equal to omega L or J omega L. Okay, Y is 1 by J omega L. J is the vector or the 90 degrees vector. Okay, because you got this plus 90, right? You can replace it by j or I. Okay, z is j omega l. Omega is again 2 pi f c, 2 pi f. Okay, omega is 2 pi f. Z is equal to j omega l. This is called as XL. XL is nothing but inductive reactance. Okay, and C, only C element, only C, only L. You'll get Z is equal to 1 by omega C or 1 by j omega C. Y is j omega C. Again, omega is 2 pi f. This is capacitive reactance. Capacitive reactance, inductive reactance, and resistance is same. Okay, all your what you call elements will behave this way. Resistor won't change. Impedance will, sorry, inductance will become inductive reactance. Capacitance will become capacitive reactance. Okay, now the series RL circuit. You see, all the what you call Ohm's law and all, what happened?
Nothing, sir.
Okay. All Ohm's law, nodal analysis, mesh analysis, all holds good in AC, except that all the resistance will be replaced by impedance. See, if this is a series RL circuit, this is how it is. V is equal to Vm sine omega t, R and L. This is XL. Okay, current flows I. There will be voltage drop VR here, voltage drop VL here. Okay, so what happens in a pure resistive network? We'll see with respect to what you call phasor diagrams. All this with respect to phasor diagrams. Okay, I'm taking my voltage vector as the what you call base. Okay, this is my voltage V. Okay, how will IR be with respect to voltage V? VR. Okay, okay. IR with respect to voltage VR. Okay, so sorry, this is a series. I'll take I as reference. Okay, I as reference. Okay, so voltage and current across a resistor are always in phase. You have to remember voltage and current in case of resistor are always in phase, right? V and I are in phase. Okay, in case of inductor, what happens? I lags V by 90 degrees or V leads I by 90 degrees. In case of capacitor, you can say the opposite. I leads V by 90 or V lags I by 90 degrees. Okay, so again, how is VR with respect to I? Current flowing through the resistor and voltage across the resistor will always be in phase. Okay, I'm not taking about the magnitude. So VR and I are in phase. So how will VL be with respect to I? Voltage and current through an inductor. Voltage leads I by 90 degrees. Okay, so voltage leads I by 90 degrees. This is VL. So the resultant of these two is my total voltage V. Okay. So the angle is some phi. Depends upon the magnitudes of VR and VL. Okay. So how is V with respect to I? V leads I by phi, or you can call I lags V by phi. Okay. In case of pure resistor, the phi is 0, pure resistor, right?
Right.
I and V will be in phase. In case of pure inductor, phi is 90 degrees. V leads I by 90, I leads V by 90 degrees. If it's an RL circuit, what happens? There will be some angle and current lags the voltage, or voltage leads, current lags the voltage, or voltage leads the current by 5 degrees. Okay. Okay.
Right, sir.
So impedance. So similarly, I can write I is equal to, or sorry, V is equal to VR plus VL, JVL. Why? Because this is an impedance term, JXL. So this is IR plus J into IXL. This is I into Z. So I will take I common. This will be Z is equal to R plus JXL impedance. Okay, I can write this as Z is Z at an angle phi. Okay, this is capital Z. Okay, so small z is equal to under root R square plus XL square, and phi is equal to tan inverse XL by R. Tan inverse XL by R. Okay, and this is phi. Okay, this is impedance in case of RL circuit. Impedance in case of RL circuit. Okay, series RL circuit. And one more point, I will define something called as power factor here. Okay, what is power factor? Definition of power factor. Okay, there are three definitions. People generally can easily explain power factor by these three definitions. I'll give you the definition first, then we'll see what all those. Okay, power factor is the angle between, oh sorry, cosine of the angle between, cosine of the angle between voltage and current. Okay, ratio of resistance to impedance. Okay, what is the third definition? One, two. Third definition is ratio of active power to apparent power. Well, I'll tell you what is this. Active power to apparent power. Just remember these definitions. Tell you the importance of power factor as well as, or the significance of power factor, and as well as the definitions. I'll explain it. Cosine of the angle between V and I, ratio of R to Z, or ratio of active power to apparent power. So here, what is the ratio of R to Z? Is nothing but R by root of R square plus XL square, is nothing but power factor. Or cosine of the angle between voltage and current, V and I, is phi. So cos phi is nothing but your power factor. Okay, you'll understand it when we deal with complex power. Okay, it's a factor of power. Okay, so it's called power factor, cos phi. Okay, power factor is R by R square plus XL square under root cos of angle between voltage and current. Okay, next, series RC circuit. So again, I have an V is equal to Vm sine omega t. This is R jXC minus jXC. And this is VR VC. Okay, and I. So again, taking I as a reference, series circuit I as a reference. What is VR with respect to I? It's in phase. Voltage and current through the resistors are in phase to each other. So VR and I are in phase. What is VC with respect to I? Current through the capacitor and voltage. Voltage lags. Remember, voltage lags I by 90 degrees. This is VC. The resultant is this one. And this is V. Angle phi. Okay, what happens here? Now V lags I by phi, or I leads V by phi. So in case of an RC circuit, voltage lags current by 5 degrees, or current leads voltage by 5 degrees. Okay. In case of a pure capacitive circuit, voltage lags current by 90 degrees, or current leads voltage by 90 degrees. Case of pure resistance, voltage and current are in phase with each other. Okay. Okay. So again, V is equal to V. Or R square plus XC square tan inverse minus XC by R. Okay. Impedances are minus JXC in case of RC circuit. Okay. See again, power factor is, as I told you, it is cosine of angle between V and I, R by Z, uh, active power by apparent power. We'll discuss it later. Okay. Cosine of angle between V and I. If voltage leads current, okay, if voltage leads current, then this is called as leading power factor. Sorry. Okay, always take voltage as reference. Taking voltage as reference. Okay, if current leads voltage, then this is said to be leading power factor. Okay, current lags voltage or the reference, this is called as lagging power factor. This is important. Taking voltage as reference. When you say power factor is leading or lagging, you only say with voltage as reference. Okay, leading power factor or lagging power factor. Okay, clear?
So always we use voltage as reference for this power
Yes.
factor, right? Okay, okay.
Yes. In case of power circuits, what usually happens is voltage is the cause and current is the effect. So that's why we usually take voltage as reference. So in denoting power factor as lagging or leading, we'll always take voltage as reference. Even if it's a parallel circuit or a series circuit, you'll always take voltage as reference. Okay.
Okay, okay.
So series RLC circuit. V equal to Vm sine omega t R jXL minus jXC. VR, VL, VC. Okay. See again, this is my I. If I draw the phasor diagram again, or vector diagram, this is my current I. Okay, VR will be in phase. Resistor voltage across resistor is in phase with the current. And what about VL? How will VL be? VL will be leading I by 90. This is my VL 90 degrees. VC will be lagging by 90 degrees. Okay, the resultant will depends upon VL minus VC or VL difference VC. Okay, if it is VL is greater than VC, the difference will be VL minus VC. If okay, VL greater than VC, right? If VC greater than VL, this will be VC minus VS. Based on that, you'll get the resultant. Okay. Okay, there is a condition where VC is equal to VL. That is something you'll see in resonance. Okay, that is something you'll see in resonance. Okay, if VC is greater than VL, the circuit is capacitive in nature. Okay, capacitive in nature, current leads voltage. Okay, if VL greater than VC, then the circuit is inductive in nature. Inductive in nature, I lags V, right? We have seen in series RL and RC. Inductive in nature, I lags V. Capacitive in nature, I leads V. Okay, at resonance, V and I are in phase because VL is equal to VC. Okay, so this is V is equal to VR plus VL minus VC. JVL minus VC. Difference VC. Okay, IR plus JI into XL difference XC. I into Z is equal to I into R plus J XL difference XC. So Z is equal to R plus J XL difference XC. Okay. Series RLC factor. Any doubts regarding this so far?
No, no.
Okay. So complex power. S is equal to V into I conjugate. Okay, S is V into I conjugate. Basically, why I take I conjugate is something like this. S is equal to V into I is generally what we take, but S is equal to V into I is your complex power. Why? Because if I say this is my voltage and this is my current, okay, this is the angle phi 1 and phi 2 should be V into I. If we want to find V into I, what I will do is write V is equal to some Vm at an angle phi 1. Okay, I is equal to Im at an angle minus phi 2. So if I write Vi, what happens? Vm Im at an angle phi 1 minus phi 2. But the difference between angles of V and I is phi 1 plus phi 2. That is why I have to always take conjugate of this. So then I'll get phi 1 plus phi 2. That is why complex power we will always take V into I conjugate. Okay, this is important. Why conjugate is taken? Okay.
So,
Hmm.
actually, if
Huh?
there is a difference, then if that affect the power actually.
Yes, it affects now. The power is nothing but the product of V and I. Okay, power is nothing but power of product of V and I, and in the flaw in taking this in this form, what you call phasor form is the phase angles are getting subtracted. So phi 1 minus phi 2 will be somewhere like this. So that is not the actual angle. So to get the actual angle, what we'll do is we'll take I conjugate. Okay, you can take V conjugate also, but usually V will be our reference. So we don't take V conjugate, we'll take I conjugate.
Okay, okay.
Okay, V into I conjugate is your what you call complex power. Okay, I can write it something like this. V is equal to Vm. Yeah, the same one I'll use it. Vm at an angle phi 1, Im at an angle phi 2. Okay, so this is for again I is lagging V, lagging power factors. Okay, lagging power factors. So Vm, Im at an angle phi 1 plus phi 2. Okay, so if I write this in complex form, what will I get? Or rectangular form will be Vm Im cos phi 1 plus phi 2 plus j Vm Im sin phi 1 plus phi 2. Right? If these are the maximum values, if I want RMS values, say RMS values. Okay. Actually, if nothing is mentioned, you can always take them as RMS values. Okay. So this can be written as P plus JQ. P plus JQ. S is equal to P plus JQ. P is VI cos theta or cos phi theta. Okay. Phi plus phi 1 plus phi 2. Okay. Q is equal to VI sin theta. Okay. S is called as apparent power VI. Okay. This is called as apparent power. P is called as active power or real power. Active or real power. This is called as reactive power. Reactive power, active power, and apparent power. Terms are important. Active power, S is equal to P plus JQ. Okay, VI cos theta plus JVI sin theta. Okay, VI at an angle theta. Okay, S is VI at an angle theta. So P is active power, reactive power, apparent power. As I told you, power factor is nothing but cos theta. And this can also be written as P by S. VI cos theta by VI, which gives you cos theta. Okay. So power factor definition is active power by apparent power. Okay. Active power by apparent power.
Is there any significance in these power in real time? Like,
Actually, there is significance. So the active power is the power for actual work done. Actual work done in any circuit. Like if it's a resistive network, the heat produced in the resistance or heat produced through the resistor. Or if it's an example of a light, the lumens output or similar one. Okay, if it's a motor, the output of the motor. is the active power. Okay. And the reactive power is sometimes called as the magnetizing component of power. That means the reactance, inductive reactance. What does inductor stores energy in the form of magnetic form, right? So this reactive power shows you the uh, reactive power. Okay, reactive power in the sense the reactance, the power stored in the reactance. This is not the actual work done. The average of Vi sine theta will be zero. Okay, no average power is ever consumed in a inductive or a capacitive circuit. Okay, capacitor only stores energy. Inductor only stores energy. Inductor stores energy in the form of magnetic, in the form of magnetic circuit, and capacitor stores in the form of electrostatic power. Okay, so they both are energy storing elements. Only resistor is energy dissipating element. Okay, all the actual work done can be represented by resistor only. Actual work done. Okay, so that is why this is called as real power or active power. P is called as real power or active power. Q is only a reactive power. It simply oscillates between the source and the load. Okay, source and the load. So that is why the power factor is called the factor by which the power or the active power is there. Okay. If I have an 100, okay, again the units, I haven't given you the units. Active power P is VI, voltage into current into cos theta, right? So S is VI, Q is VI sin theta. Again, this is watts, voltage into current, volt amperes. Okay. Apparent power is measured in volt amperes. Active power is measured in watts. Reactive power is measured in VAR, volt amperes reactive, VARs. Okay. VA, VAR, and W. Okay. If it's in milliwatts, milli VA, milli VAR, or kilowatts, kilo VA, kVA, kVAR, kW, kVA, kVAR. Okay.
In household connection, it is shown as a 3 point at the load, like a
I'm not able to hear you properly. Can you be a bit louder?
uh, in our household.
Uh,
Hello.
yes, yes.
Uh, the connected load is shown. That kind of thing. Uh, is it active, reactive, or that anything related to that?
Yes, yes. Household power. Um, Generally, there is one more concept you have to understand. So, as I told you, S is equal to P plus JQ. Okay. All your sources, energy sources like the generator at your power station will generate S. Okay. In that, only P is the active one. Q doesn't do any work. Okay. But if you don't maintain Q as zero, what happens, your reactive power, if you don't nullify your reactive power, it consumes major part of the S and it won't be able to supply P. That is why in your electricity bill you will be saying kilowatts. Okay, kilowatt hours, basically energy is kilo power into time, right? Kilowatt hours. Okay, so kilowatt hours is the active power. kVAH is the what you call the apparent power. Okay, S, apparent energy, right? Okay, this is the active energy and this is the apparent energy, because kWh is nothing but 1 unit of electricity. Okay, 1 kWh is nothing but 1 unit of electricity. Okay,
Is
you'll be
the is the apparent power the same as something called a demand or something?
no, no, that is, see, demand is the power thing, maximum demand is the power thing, and this is what kWh is, your energy. Maximum demand is the total, what you call the maximum of the total power you are consumed in that month or that year or that given period of time. It is a maximum of all those. It's a maximum demand or the demand, you can call it that way. Okay, it can be kilowatt, kVA. or kW. Okay, mostly it will be kW, not kV. Yeah. Okay.
Okay, it depends upon our history of usage, maybe, right?
Yeah, it depends upon your history of usage or the connected loads. Okay, all it depends upon many other things. Basically, it shows the maximum. If it's in summer, you'll use your ACs. If it's your winter, you'll use your geysers. That's how. It depends upon the month which you use and all. Okay.
Okay, great.
So simply obtain power factor for the following circuits. See, solving AC circuits is similar to that of DC circuits like the resistive networks. Only thing is your R is replaced by Z impedance. Okay, okay. So you have to understand and do it accordingly. See, I can you need calculator to solve many of these problems. That's why I don't expect you'll be getting these kind of problems in your HAL at least. Okay, HAL exam you won't be getting because these involves lot of complex calculations, right? But I'll give you an example first. Let me do this one. J5 and minus J2 are in series, right? Directly you can add or subtract these terms, but 4 is a real term. Real and imaginary terms cannot be added directly. So this will be 4. This is minus J2. So J5 minus J2 is obviously an inductor value J3. J5 minus J2 is J3. So J2 and J3 are in parallel. J minus J2 and J3 are in parallel. So again, R1, R2 in parallel is R1, R2 by R1 plus R2. So similarly, or Z1, Z2 by Z1 plus Z2. Similarly, this will be like this. Minus J2 into minus J plus J3 divided by minus J2 plus J3. So minus J square is minus 1, I square is minus 1, and J square is minus 1. So this will be 6 by J, right? 6 by J or minus J6. Minus J6. So this can be replaced by minus J6. So Z is equal to 4 minus J6. So how do you define power factor? Power factor is the ratio of your 3 R by Z cos of angle between V and I or E by S. 3 definitions. Always remember 1, 2 and 3. 3 definitions. So this is R plus J, R minus JXL, right? So this is R is 4 by under root 4 square plus 6 square. What is the value? 4 by 36 plus 16. What is the 6 square? You tell me the value. 4 square plus 6 square under root.
Root 52.
Right? Okay.
I have one doubt in that previous thing, previous circuit. J5 and minus J2. So actually,
This one.
uh, I cannot see. Oh, okay, okay. The rounded, yes, the same thing.
Hmm.
J5 minus J2. Actually, so one is inductor and one is capacitor. So inductive reactance, uh, L omega, and another one is 1 by J omega C.
Hmm.
So we should use that or something.
No, I didn't understand. Can you tell me? Can you ask me the repeat the question?
Like so is J5 is the inductor value, inductance value.
Okay. See, whenever you see it in terms of J, these are all ohms.
Okay,
Okay.
okay.
Okay. J omega L or J XL, J XC minus J. See, capacitance, you'll always have minus, right? Minus J XC or 1 by J XC. Okay. In these two forms, it's a capacitor. JXL is always an inductor. Okay, this is inductive reactance. This is capacitive reactance, not inductance or capacitance values. These are inductive reactances and capacitive reactances.
Okay. And
Okay, 4 by root 52.
it can be
Right, the
treated.
answer as per factor. Okay, now tell me whether it's lagging or leading. You can always see this is minus J6. What kind of element is this? Can you tell me?
Ca- capacitor.
Right, capacitance. You'll always get minus J for capacitance. So this is a capacitive circuit. Resistor and RC circuit, always power factor is leading. Okay, remember, that's what I told you, right? Yeah. V has difference. For I leads V leading power factor. So this is for capacitance. Capacitive circuit always current leads voltage. Current lags voltage is inductive circuit. Okay. So power factor is leading here. Why? Because this is a capacitive circuit. Z in Z you can directly say. Okay. Or if I calculate the current, I'll get plus 5 because V is reference. If I get current leading, it's always leading power factor. Okay. Shall I repeat? Am I going fast?
No, no, no.
Okay, clear, right?
Clear, clear.
Okay, this is how you'll have to do the calculation for capacitance, sorry, power factors. Okay. So similar one, it takes a bit of time. Again, series, parallel, series, and parallel. Okay, if it's a resistor, you can directly do them, but these are complex values, so you have to use your calculators or the techniques polar to rectangular form and rectangular to polar form, and you have to find those. Okay, and similar one, power factor and average power for the following. Okay, so you have to find P. P is nothing but VI cos theta. Okay, theta is nothing but angle between V and I. You have to find cos theta is nothing but your power factor again. Okay, you have to find voltage is given 30, find current I. You'll get, okay. Or otherwise, I'll do the first one. Okay, this parallel combination 4 and J2 are parallel. 4 into minus J2 by 4 minus J2. Okay, you can find it. Okay, this is 4 plus J2 divided by 4 plus J2. Okay, you'll get minus J8 to 4 plus J2 divided by 4 square plus 2 square. So this is minus J into minus J square plus this is 216 by 4 square 16 plus 420. Okay, this is how you get 2 4 16 4 by 5 minus J 8 by 5. This is your resistance up to this point plus the 6. Impedance will be this plus 6. Okay, so Z is equal to 6 plus 4 by 5. 5 6 30, 34 by 5 minus G 8 by 5. Okay, this is a capacitive circuit. That's why you got it as minus. So current IR, let me write it in this way, under root 34 by 5 square plus 8 by 5 square. Find the value of this.
So actually, from where this 34 by 5 came?
Okay, see this value is only this part, right?
Okay, okay.
Okay, and to get impedance, what should I do? I should add 6 to this because this is in series with this. Okay,
Okay.
so 6 plus 4 by 5 is 6 5 35 30 plus 4 by 5 35
Okay.
34
Okay.
plus the imaginary term. .98, okay, at an angle something. Okay, so power factor cos theta can also be written as 34 by 5 divided by 6.98 R by Z.
So it means sum of all the real parts by that 6.98 impedance.
Yes. Okay, you will get some angle or cos theta, some value which is leading. Power is VI cos theta. Okay, I is again 30 at an angle 0 by Z. Okay, you have to find VI cos theta is a power. You need your calculators to solve this. I'm just giving you the example to solve this. Okay. In the given circuit, the voltage VL has a phase angle of dash with respect to VS. In the given circuit, the voltage VL, this is VL, has a phase angle of dash with respect to VS. Try to solve this. In the given circuit, the voltage VL has a phase angle of dash with respect to VS. See, for this, you need to understand this. This is my current I, series R circuit. So I'll take I as reference because series circuit current is same. Okay. So I'll call this as VR and this is VL. So VR will be in phase with I. VL will be 90 degrees leading. Okay. So the phase angle between, so this is my VS. I need to find the angle between these two. Okay, what is this angle? This angle is power factor angle, right? VS and I, angle is power factor angle. Okay, so this will be 90 minus 5, power factor angle. Okay, what is power factor here? So Z is equal to R plus JXL or under root R square plus XL square. Okay, under root 17.32 square plus XL square. What is this? (300 plus 100) under root 400. 20. Z is 20. So cos theta is R by Z. Okay, R is 17.32 by 20. How much is this? 17.32 by 20. 8.66. So theta is, sorry, 0.866. I'm sorry. 0.866. Again lag. Okay, theta is cos inverse of this. 30 degrees. Okay, theta is 30 degrees. What is the angle between VL and VS? 90 minus 30, 60 degrees. Okay, clear? Clear, right? Okay.
Okay.
Next, the power dissipated in the circuit shown in what happened?
I cannot see the slides.
Can you see the slide now? Am I audible? Now, see the total power dissipated in the circuit is 1 kilowatt. The voltmeter across the load reads 200 volts. The value of XL is dash. You need to find the value of XL. Okay, the volt. This is the voltmeter. It reads the load value as 200 volts. Okay, and the power dissipated is 1 kilowatt. So you have to find the value of XL. Am I audible? Are you able to see me, the screen?
Yes.
Okay. See, for these kind of questions, you have to understand the concept is 1 kilowatt is the power dissipated. The power only gets dissipated in the resistors because L and C elements are what you call energy storing elements. Energy storing elements, only resistor power gets dissipated. Okay, so 1 kilowatt or 1000 watts is dissipated in only resistor. Where are the resistors? This is one resistor and this is one resistor, right? So total of 10 amps is flowing here. Here it is 2 amperes, and here this will be again 10 amperes, right? This is a voltmeter. Okay, so these two are in series. 10 amps flows through this, right? So what is the power dissipation only in these two elements? Okay, total power is P1 ohm plus PR, okay, which is equal to 1000. P1 is I square R. Current is 2 amperes, resistor is 1. So 2 square into 1 plus PR. Okay, I can write it as I square into R. 2 square is 4 plus I is 10 here. 10 square is 100 R. It's 1000. Can you find the value of R? R is nothing but 996 by 100. Right? Is 9.96 ohms. You found R. You have voltage V, current here. So impedance of load. Okay, this is load, right? So V is 200. Writing it V by I. V is 200, current is 10. So this is 20 amperes. Sorry, 20 ohms. Impedance. You have resistance of load. You have impedance of load. Can you find XL? XL is nothing but under root ZL square minus R square. 20 square minus 9.96 square under root. This will be XL. Understood? Or shall I repeat?
Clear.
Shall I repeat?
No, no.
Okay. Some 17.3 ohms. Okay. In the figure, the admittance values of the elements in Siemens are YR, YL, and YC are given. The value of I as a phasor when the voltage E across the element is 10. Okay. So again, a simple one. So total Y is equal to YR plus YL plus YC. Admittances, right? You can directly add them. 0.5 minus J 1.5 plus J 0.3 will be 0.5 minus J 1.2. Okay, so E is given, you know Y. Okay, see V is equal to I into Z, or V is equal to I by Y. Okay, I need I is nothing but the value of I as a phasor when voltage across is 10. I is nothing but E into Y, or Y, V into Y. E is given as 10 at an angle 0 multiplied by 0.5 minus J 1.2. 10 into 0.55 minus J 12. Okay, direct questions. You can see and answer these. See and tell the answers. Clear?
Clear, clear.
Try to solve this in the circuit shown. The power consumed by 5 ohm resistor is 10 watts. Then the power factor of the circuit is dash. Power consumed is given. Find the power factor. Power consumed in the 5 ohm resistor is 10 watt. Find the power factor of the circuit. Any answers? Any guesses how to solve this? It's an RL series circuit. Power factor, definitions of power factor. Tell me the definitions of power factor. You have three definitions, right? What are those? Definitions of power factor. R by Z. Okay. Cosine of angle between V and I. And P by S. real power to apparent power. Three definitions of power factor: R by Z, cos VI, P and S, P by S. Okay. So it is given that power is consumed by the 5 ohm resistor is 10 watts. Okay. The power consumed P5 is 10 watts. Okay. So power is nothing but I square R is 10 watts. So what is I? I is 10 by R under root. 10 by 5 under root. Root 2 is current. Okay. You have voltage. V and by I is nothing but Z. Okay, this is maximum value. Take the RMS value. RMS value of sinusoid is 50 by root 2 by I is root 2. This will be 25 ohms. Z is 25 ohms. Okay, I have the total resistance. R is 5 ohm plus 10 ohm, 15 ohms. I got R, I got Z. Cos phi or power factor cos theta is R by Z, 15 by 25.
One.
Understood? Shall I repeat? Understood?
Yes.
Okay. So similar one, reactive power drawn from the source. Okay, this you again, reactive power is nothing but Vi sine theta. Okay, so sine what is J10 minus J10 X L difference XC is 0, right? 0 if X is 0, Z is equal to R square plus XL square, XL minus XC whole square or X square under root. If X is 0, Z is equal to R. Power factor cos theta is R by Z. R by Z is 1. Cos theta is 1. Sin theta is, if cos theta is 1, sin theta is 0. So Vi sin theta is 0. Apparent power is, or sorry, reactive power is 0. Okay, when the X term is 0, reactive power is 0. What happened?
Clear, clear.
Okay, when the X term is 0, the reactive power is 0. Okay, moving on, next one. In AC circuits having R, L and C and operating at lagging power factor, increase in frequency will result in dash of current. AC circuit having R, L and C and operating at lagging power factor. That means R plus JXL. It is in the term of XL. XL minus XC, right? Okay, XL is dominating. So this will be R plus JX, not minus. Okay. This is how it is. That means lagging power factor. Okay, now if I increase the frequency, see, this is nothing but omega L minus 1 by omega C. If I increase frequency, what happen? This term will decrease. Okay. This term will decrease and this term will increase. So the difference will increase. Difference will increase. Impedance increases. Current decreases. Okay, I is equal to V by Z. Impedance increases, current decreases.
Lagging means the effect will right.
Lagging means, yeah, it will be mostly inductive in nature, plus J. Okay. The XL minus XC is omega L minus 1 by omega C. If it's capacitive in nature, it will be XC minus XL. And this will be minus. Okay, this whole term will be negative. Inductive in nature, XL minus XC is positive. Okay.
Okay.
We'll continue in the next class. Theorems, basically all done network analysis we done in DC. We did in DC circuits or the resistive circuits like source transformation techniques. Okay, Norton's theorem, Thevenin's theorem. Okay, what else? Superposition theorem. All will hold good in case of AC, except maximum power transfer theorem. It also holds good. There will be certain conditions we'll see in the next class. Okay, except for MPTT also holds good maximum power transfer theorem, but there will be some more conditions in it because this is an AC circuit. We'll see that in the next class. Okay. Okay. So far clear in today's class.
Clear, clear, sir.
Okay. I'm concluding the class. Okay.
Thank you, sir.
Thank you.